Hi viewers, welcome to my class on mechanics of materials. In today's class, we'll work out some numerical examples on compound stresses. Let us start. At a point in a strained material, the normal stresses 45 MPa compressive and 60 MPa tensile are acting along x and y directions. If the shear stress associated with the planes is 34 MPa as shown in figure, find the following. First, normal and shear stress on a plane inclined 40 degree with the horizontal. Second, principal planes and principal stresses. And third part, maximum shear stress and its planes. Sketch the principal stresses on a properly oriented element. So in a strained material, in the x direction 45 MPa compressive stress is acting, and y direction 60 MPa tensile stress, and it's also associated with the shear stress of 34 MPa, and on the right face it's downward. So in the analytical solution we have to treat this as negative. So we have sigma x minus 45, minus because it's compressive, and sigma y 60 MPa tensile, so positive, and tau xy minus 34 MPa. Since it on the right face it's downward, it is minus. You have to find out the normal and shear stress on a plane inclined 40 degree with the horizontal. So the plane is shown here 40 degree with the horizontal. So this plane inclination from the vertical is 50 degree. 90 minus 40, so that gives 50 degree. That is the inclination of the plane from the vertical. So theta is 50 degree. And next you have to find out the principal planes and principal stresses and maximum shear stress and its planes. So let us find out the normal and shear stress on a plane inclined 40 degree from the horizontal. That is, for theta is equal to 50 degree. Now to find out the sigma, you can use this equation, sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Now substituting theta is 50 degree and the stress values, you will get the normal stress on that plane. So sigma x you have minus 45, sigma y plus 60, so minus 45 plus 60 by 2, and sigma x and sigma y will substitute, minus 45 minus 60 by 2, the cos theta is 50, so cos 2 into 50 minus tau xy is minus 34 sin 2 into 50. So you get sigma as minus 16.867 megapascal. This is the normal stress on this plane. So normal to this plane, the stress acting is compressive, minus indicates compressive, 16.867 megapascal. So on this plane you have compressive stress. Now to find out the shear stress acting along this plane, you can use the shear stress formula. Tau is equal to sigma x minus sigma y by 2 sin 2 theta minus tau xy cos 2 theta. Substituting for sigma x and sigma y, get minus 45 minus 60 divided by 2 sin theta is 50 sin 2 into 50. Tau xy is minus 34, so minus of minus it will make plus, plus 34 cos 2 into 50. So that will give tau as minus 57.606 megapascal. So that is a shear stress acting on this plane. So this minus doesn't have much significance here, only numerical value is important in this case, because shear stress will be acting like this. Minus indicates and this part of the element is exerting a force downward on this. So this shear stress will be downward here, and this part will be exerting an equal amount of shear force on this, so that it will be acting upward. So shear stresses will be acting downward from here and upward from here. So that is the minus sign. So this direction, even if the direction changes, the magnitude of the shear force is significant there. In analytical calculation, to get the normal stress sign, that is whether it's compressive or tensile, this sign is important. Applied shear stress, if you change the direction, the normal stress value will change, that magnitude will change. So you got the magnitude of the shear stress as 57.606 megapascal. Now let us find out the principal planes. Principal planes you can find out as tan 2 theta p is equal to 2 tau xy divided by sigma x minus sigma y. So it is equal to tau xy is minus 34. So 2 into minus 34 divided by sigma x is minus 45 minus sigma y is 60. So you will get 2 theta p is 32.92 degree, or theta p1 is 16.46 degree. Now after getting theta p1, you can find out the second principal plane. So this is one of the principal plane, 16.46 degree from the vertical in the anti-clockwise direction. So after getting this, you can find out the second principal plane by adding 90 degree to that is 106.46 degree. So these are the principal plane which are mutually perpendicular. Now let us find out the principal stresses. Principal stresses you can directly find out using the formula sigma 1 and sigma 2 is equal to sigma x plus sigma y by 2 plus or minus root of sigma x minus sigma y by 2 square plus tau xy square. So the direct formula exists, but at the end we have to plot the principal stresses associated with these planes. So this particular plane, which stress is acting, what is the normal stress, that is principal stress acting, that you have to show. So when you are finding out using the direct formula, we will not know on this principal plane whether sigma 1 or sigma 2 is acting. So to identify that the principal stress associated with this particular plane, you need to use the normal stress equation and substitute this angle. So you can use normal stress equation, substitute the principal plane, that is 16.46 degree, and when you substitute theta as 16.46, you will get the normal stress associated with that plane, and which is the principal stress, one of the principal stress. So you are using the normal stress equation, normal stress on a given plane, and we know the one of the principal plane. Substitute that angle, you get the principal stress associated with that particular plane. So you have substituted sigma x and sigma y, and again sigma x and sigma y, and the theta is substituted as 16.46, one of the principal plane, and tau xy is minus 34. You get sigma 1 as minus 55.048 megapascal. So that means on that particular plane, 16.46 degree plane, you have a compressive stress of magnitude so much, and this is the one of the principal stress. To find the other principal stress, you can substitute this angle as 106.46, because other principal plane is 106.46. You can substitute that angle as 106.46. Instead of doing that, we know that sum of the normal stresses on any two mutually perpendicular planes is a constant. We have proved that one of the earlier classes, that the sum of the normal stresses on any two mutually perpendicular planes is a constant. Since the principal planes are mutually perpendicular planes, the summation of the principal stresses is also equal to a constant, and that is equal to sigma x plus sigma y. So we know sigma 1 plus sigma 2 is equal to sigma x plus sigma y, or sigma 2, the second principal stress, can find out as sigma x plus sigma y minus sigma 1. So sigma 1 is known, sigma x is minus 45, sigma y is plus 60, minus sigma 1. minus of minus plus 55.048. So we'll get sigma 2 as 70.048. So this is the principal stress associated with the principal plane 106.46 degree. So you identified which principal stress is associated with the principal planes. If you use the direct formula also, you will get these values, but to identify which stress is acting, which principal stress is acting on which principal plane and plotting will make it difficult. Now let us find out the planes of maximum shear stress. So planes of maximum shear stress you can find out using the formula tan 2 theta s is equal to minus sigma x minus sigma y divided by 2 to xy. So minus of sigma x is minus 45, sigma y is 60 divided by 2 into minus 34, so xy is minus 34. So you'll get 2 theta s is minus 57.08, or theta s1 is minus 28.54, and after getting theta s1 you can find out theta s2 as adding 90 degree to this, that is 90 plus minus 28.54 or 61.46 degree. So these are the planes of maximum shear stress. You can also find out these planes of maximum shear stress by adding 45 degree to the principal planes. Adding or subtracting 45 degree to the principal planes, you will get the planes of maximum shear stress. So we got the planes of maximum shear stress. Now to find out the maximum shear stress, you can use this equation, plus or minus root of sigma x minus sigma y by 2 square plus 2xy square. And sigma x and sigma y, you know, 2xy is also known. So substituting that, we will get tau max as plus or minus 62.548 megapascal. So on both the planes of maximum shear stress, you are getting the same value of maximum shear stress as 62.548 megapascal. Now you got the principal planes, principal stresses, planes of maximum shear stress and maximum shear stress. Now you can plot principal stresses values on a properly oriented element. Now principal plane you identified from the vertical, it is 16.46 degree. So you take a small element within the material, you take a small element with one of its sides inclined 16.46 degree. So that orientation of one side of that element you have to keep 16.46 degree, that is the principal plane. So this is one of the principal plane, and normal to that principal plane you have a compressive stress, that is a principal stress 55.048, and that is compressive. So you have to take that one side of that element at an angle 16.46 degree and show this element, and on this principal plane you have identified the principal stress as 55.048 megapascal. Show that compressive stress. Now perpendicular to that is another principal plane, so that you know principal plane is perpendicular to that. So 90 degree to that, that is from this principal plane 90 degree you have another principal plane. There you have stress as 70.048 megapascal, tensile stress. So this angle is 106.46. So that principal plane, this is another principal plane, and that plane the tensile stress is acting. Along with this, there will not be any shear stress associated on these planes. On principal planes you have no shear stress. So that is the importance of principal planes. Now you have shown the principal stresses on a properly oriented element. Now let us work out another example. At a point in a strained material, the normal stress is 120 megapascal tensile and 70 megapascal compressive are acting on two mutually perpendicular planes. If one of the principal stress is limited to 140 megapascal tensile, find the other principal stress. Also find the shear stress acting on the given planes and the maximum shear stress. So at a point in a strained material, normal stresses 120 megapascal tensile and 70 megapascal compressive are acting on two mutually perpendicular planes. So you can take whichever direction, x direction you can take 120 megapascal, y direction you can take 70 megapascal. So even in x direction you can take 70 compressive and y direction you can take 120 tensile. It doesn't matter x and y direction, you can take whichever stress you want, you can take. So that's not going to make any difference in the this solution, but the stress on a given plane will change. So if you are taking this in the x direction on this particular plane, on the stress values depends on this direction, but principal stresses and principal planes are not going to be affected by these directions. So you are given the one of the principal stresses, it's limited to 140 megapascal. We have taken sigma x as 120 megapascal, sigma y is then minus 70 megapascal, and one of the principal stress is given as 140 megapascal and it's tensile, so plus 140 megapascal, and you have to find out sigma 2, that is other principal stress, and shear stress associated with these planes, tau xy, and maximum shear stress. One of the principal stress is given, let us take it as sigma 1. Now principal stress sigma 1, you can write it as sigma x plus sigma y by 2 plus root of sigma x minus sigma y by 2 square plus tau xy square. So sigma 1 you know 140 megapascal, so it's equal to plus 120, sigma x is 120, sigma y is minus 70 by 2 plus 120 minus 70 by 2 square plus tau xy square. Tau xy is unknown, so you get 140 is equal to 120 minus 70, 50 by 2, 25, plus this 120 plus 70, 190 by 2, that is 95 square plus tau xy square. So now taking 25 to the left hand side, you get 140 minus 25, you get 115. 115 is equal to root of 95 square plus tau xy square. Squaring on either side, 115 square is equal to 95 square plus tau xy square, or you get tau xy square, and then you can solve for tau xy, and tau xy you get as 64.807 megapascal. So if shear stress is 64.807 megapascal, you will get one of the principal stress as 140 megapascal. So once you know tau xy, you can find out sigma 2 by using a minus sign instead of plus. If you use minus sign, you will get sigma 2. But instead of using this equation, you have another shortcut method to find out the second principal stress. We know summation of the principal stresses are going to be a constant. You can use that equation, sigma 1 plus sigma 2 is equal to sigma x plus sigma y. For any two mutually perpendicular planes, summation of the normal stresses is equal to a constant, and that is given by sigma x plus sigma y. So since principal planes are also mutually perpendicular planes, you can sum up sigma 1 and sigma 2 and equate to sigma x plus sigma y. So sigma 2 is equal to sigma x plus sigma y minus sigma 1, and sigma x is 120, sigma y is minus 70, and sigma 1 is 140, which will give sigma 2 as minus 90 megapascal. So second principal stress is compressive minus 90 megapascal. Whenever you have a compressive stress, one of the principal stress should be compressive. So you have tensile and compressive. So one of the principal stress should be tensile, maximum tensile, and another principal stress should be maximum compressive. Now to find out tau max, you can use tau max as sigma 1 minus sigma 2 by 2. Take the difference between principal stresses and divide by 2. So the principal stresses, this is one of the principal stress. Another principal stress is minus. So when you take the difference of these two, the first term will cancel, second term will add up because you have minus sign here. So this minus minus, that will make it plus. So you will get 2 times of this, and dividing by 2 you are getting tau max. So you can get tau max as sigma 1 minus sigma 2 by 2. So that is equal to sigma 1 is 140 and sigma 2 is minus 90. So minus of minus 90, you get plus 90. So 140 plus 90 by 2, or 230 by 2, or 115 megapascal. So this is a maximum shear stress acting on this element. So we got the second principal stress, shear stress associated with these planes, and maximum shear stress. That's all for today. Thank you for watching.